It's just a small chunk of metal, maybe the size of your thumb. But it's traveling faster than the speed of sound. It spins, it tears, it punches through steel, and it's designed to destroy. Now imagine stopping that with fabric. Not with steel, not concrete, but threads, woven tighter than a spider's web, engineered to do something that feels almost impossible. From SWAT teams to school bags, bulletproof materials are everywhere. But here's the burning question. How do they actually work? When most people picture bulletproof armor, they imagine something hard. Plates, shields, maybe even something futuristic. But the most common form of protection? Soft armor. Flexible, fabric-based, and incredibly effective. The star of the show is Kevlar, a synthetic fiber 5 times stronger than steel by weight, but it's not magic, it's science and engineering. When a bullet hits, it doesn't just pierce, it pushes, and Kevlar pushes back. The key isn't hardness, it's resistance to deformation. Kevlar stretches, absorbs, and spreads the bullet's energy over a wide area, turning a direct hit into a distributed shock. We've been trying to stop projectiles since the dawn of war. From wooden shields to iron breastplates, the idea was always the same: meet force with force. In medieval times, plate armor stopped arrows and blades. But then came the gun, and suddenly, even the thickest metal wasn't enough. By World War I, soldiers wore flak jackets, designed not to stop bullets but to deflect shrapnel. It wasn't until the 1960s that DuPont introduced Kevlar, and body armor as we know it began to evolve. Let's break down the threat. A bullet is small, but it carries a lot of energy. It's not just its speed, it's the energy focused into a pinpoint. Energy equals 1/2 of mass times velocity squared. And that squared velocity makes a big difference. When a bullet hits soft tissue, it creates a temporary cavity, a violent ripple effect, far beyond the actual path of the bullet. So the challenge isn't just stopping the bullet, it's stopping the energy. Kevlar armor doesn't rely on a single barrier. It uses layers, usually 20 to 40, each with a job. The first few layers catch and begin deforming the bullet. Then comes the hard work, spreading that force. Think of it like crowd surfing. No one person takes the full weight, it's distributed. Each layer stretches, disperses energy, and passes it along. Kevlar fibers are tightly aligned, which makes them hard to tear. But more importantly, they slow down the projectile without needing to be rigid. It's like dropping a bowling ball onto a trampoline. The impact spreads, the material strains, but it holds. Soft armor has its limits. It's great for handgun rounds, but rifles, that's another story. Rifle rounds move faster, they're pointed and often jacketed and designed to pierce. Enter hard armor, typically made from ceramics layered with composite backings. The ceramic layer fractures the bullet, breaks it into pieces, then the backing catches the fragments. It's a 2-step system: destruct and absorb. But even this has trade-offs. Ceramic plates are heavier, bulkier, and often only rated for a few hits before needing replacement. So what's next? Researchers are pushing beyond fibers and ceramics into realms that sound like science fiction. Liquid armor, for example. It stays liquid when calm, fluid, but hardens instantly upon impact. It's based on shear thickening fluids that react to sudden force. Others are experimenting with carbon nanotubes, graphene foams, and smart textiles that can sense threats and stiffen in real time. The goal? Make armor that's lighter, stronger, and maybe even invisible to the wearer. So how do bulletproof materials actually stop bullets? They don't act like walls, they act like traps. They stretch, absorb, and redirect the very force meant to destroy. What once took plates and iron now fits under a hoodie. It's not just protection. That's engineering. That's physics in action.